All right. Good morning, everyone, or I hope it's morning. This is going to be the first recitation using the online format for this semester, and I hope this is all finding you in good health. As we're all trying to adjust to this, I would please or really appreciate your comments and let me know if this works best for you. I would prefer this to just be uploaded on Friday so that way you can watch it at your earliest convenience. But if this doesn't work for you, let me know and we can adjust accordingly. So today in this recitation, we are going to go over stress distribution, a little bit of settlement calculations, and things of that nature. For this format, I am going to post videos to Canvas using the Kaltura platform. But in case that doesn't work, I am also going to post to my YouTube page here with the magnificent bear and the Nevada landscape. So on with the show. Not going to annotate. There we go. We're going to move it right there. So the first problem we're given is, get my pen all ready. Great. So we are going to estimate the ultimate consolidation settlement under the center line of this foundation. The mat is 1.2 meters thick of reinforced concrete, and the average stress on the surface of the slab is 80 kPa. We have this soil profile given to us and these values given from an odometer test, which an odometer test is just the same thing as a consolidation test. So first thing we are going to do, so I get situated, is that we are going to assume the unit weight of concrete, which is just a typical value, and we're going to say 23.6 kilonewtons per cubic meter. So next we're going to find an initial load, which is going to be the weight of the foundation plus the load being applied. Or basically it'll be an initial bearing capacity. So we have 23.6 times 1.2 plus the 80. So therefore, you'll get Q naught equals 108.3 kPa. But now we need to find the load being applied, that is net load. So we're going to say Q net equals 108.3 minus, and I'm going to come down here, 1.9 times 9.81, which I'm using this because this is the soil layer around the foundation, times 1.2. So therefore, our net load equals 85.9 kPa. So there we go. We've officially started this problem. So we're going to use the Boussinesq method to solve this problem, which down here, as you can see, I'm going to change this to red. And here is our equation. And I'm using equation 10.9 out of your guys' textbook to solve this problem. And this is the figure also given from your textbook that we're going to use to determine these two factors. And these factors are interchangeable, but they're based on the dimensions, which I'm going to draw down here, of, that's a very not square. All right, third time's a charm. There we go. So this is our foundation mat, and it's saying, all right, we got 17 by 17. And we need to know the stress distribution underneath the center of our foundation. So our M is going to be 8.5, which is a 17 over 2, over Z. And we need to find Z at different depths underneath the foundation. And for N, we're going to get 8.5 divided by Z. So this is a big chunk of what we're going to do later on in the problem. So now we're going to find our void or initial void ratio so we can find some other parameters. And we're going to use this equation, which we're going to assume our specific gravity is 2.7, and we're given that the water content was 42%. So we're going to say 0.42, and we are going to assume full saturation. So therefore, we get a void ratio of 1.13. Now, using these parameters, these parameters are gathered from your consolidation test. And we're going to adjust them a little bit using the void ratio so that they're in relation to strain. And this is your compression curve index, and this is your swell or recompression index value. So using those values, we are going to find C sub C of strain, which will be C sub C over 1 plus E naught. And we are going to say, well, 0.4 divided by 1 plus 1.3 equals 0.187. And now we're going to say C sub R sigma, which R and S are used interchangeably, just so no one's confused. And we're going to say C sub R or C sub S, same thing, over 1 plus E naught equals 0.03 over 1 plus 1.13. And therefore, we get 0.014. So now we have that, and from this soil, we can see, and a little bit of an assumption, that we have a normal consolidated clay. So to use normal consolidated clay, we are going to use equation 10.15. And that's where we come down here. And we are also going to break up the soil underneath the foundation into multiple sublayers, as you can see in this table. So I'm readjusting my papers. So we're going to say we have top and bottom of each sublayer. We're breaking up into 4 so that we can assess it here, because we don't know. We're going to assume that this sand layer is a very dense, not very permeable layer. So it acts something similar to bedrock. So we're not going to assess this. So using what we have, we're going to say, well, from 0 to 2, the center of that sublayer is at 1 meters. Sublayer thickness is 2 meters, and I'll explain a little bit more of how we are going to get these values. And then we keep breaking it up for each layer. So for this first sublayer, I'm going to go through some of the calculations. And what we're going to figure out first is our initial vertical stress, effective initial vertical stress, which will be 1.9 times 9.81 times 5 plus 1.8 times 9.81. So now it's in unit weight, but we're also going to subtract out 9.81 because it's underneath the water table. And then let me make sure I'm doing this correct. And then we are going to say times a depth of Z, because we don't know where yet. And coming down. So our sigma V naught equation is going to be 93.2 plus 7.85 Z. So we have this equation, and now we're going to go up to the center of our first sublayer. Well, we know that it's at a distance of 1. So we're going to say this Z is 1, where we will get a pressure of 101.5 kPa. So, and even at this sublayer, we're going to bring back our M, and we're going to say 8.5 over 1, which gives us 8.5, which also equals N. So now we're going to come back up to this equation. So we have our values of N, and we know 8.5 is somewhere here, and we know we have an N or an M that is significantly great. So we're going to assume that it's up. This is the M line that we're going to use up to infinity. So we're going to just come, oop, that's not straight at all. So wherever this line hits, we're going to bring it over, and then that's how we're going to find our I value. So once we use that figure, we find that our I value equals 0.25 for this sublayer. So now we're going to use our Boussinesq equation right up here. So, and I believe I forgot one symbol in this equation. We're going to throw in delta. So delta sigma z. So delta sigma z equals 4q net times I. So we know everything. We know 4 times 85.9, and now times our 0.25, and we get delta sigma z as 85.9 kPa, because it's just 4 over 1/4, so we get the same thing. So we're going to keep reiterating this for every layer. And we have our sublayers up here lined out. So I'm going to run through those equations real quick. So I'm going to denote this as 1. So delta sigma 2, well, so now we know the M, which also equals N, is 8.5 over 3, which equals 2.83. So now the equation is going to be 4 times 85.9. Oops, get back to my pen. Like I said, you guys will have to bear with me a little bit as I'm learning all this stuff. All right, so 84.9, sorry, 85.9 times, and then when we go through our chart, we will find that the second I value will be 0.243 approximately. So 0.243, and then we get 83.5. So now sigma equals, so we got M now equals 8.5 over 5.5, which will give us 1.545, and that I will equal 0.2175. So we will get 4 times 85.9 times this value, which will give us 74.7. And now we're going to say, well, n equals m, which equals 8.5 over 8.5, which equals 1. So I will equal 0.177. So of our fourth layer, we get, oops, I already wrote that. So we get 4 times 85.9 times 0.177, which equals 60.8. And these are all in kPa. And you can see that we're effectively decreasing in stress and change of stress as we go deeper into the soil strata. So the next thing we are going to do is that we're going to find our final vertical stress. So sigma prime VF equals sigma prime V naught plus the change in sigma V. So we get 101.05 plus 85.9. This is for this first soil layer, which equals 186.95 kPa. And we're just going to repeat this for every layer. So once we repeat that every time, we are going to get these values. So now we're at the point of the problem where we're almost done and we can start calculating the settlement. And we're going to calculate the settlement using this equation, which is very similar to up here, but we already calculated this first term. So we're just going to replace it from what we solved up here to simplify things. So now we have this, and we have our recompression curve and our virgin curve, and then our change in thickness. So, the change in thickness we will calculate. So we have this, and we're going to start at, I'm going to draw it up here, at 2 meters. So SC, well, it's going to equal 0.187 times the 2 meters, because we're assuming double drainage. Sorry, single drainage time, the log of 101.05 plus 85.9 divided by 101.05. So when we do that, we get 0.01 meters. And we're going to repeat it at 4 meters, which will be SC equals 0.187 times 2 log of 116.74 plus 83.5 divided by 116.74, which we will get 0.0876. And we're going to repeat at 7 meters, which SC equals 0.187 times 3 log of 136.4 plus 74.7 and then 36.4. So we get 0.1064 meters. And then we'll just do the same thing at 10 meters. And then at 10 meters, our SC, once we do the math, equals 0.0785. So once we've determined all of this, we are just going to add them up. So SC total will equal 0.2825 meters. And this is really small, and we want to report it in something that's somewhat meaningful, so we're going to change it to millimeters. So we get 283 millimeters, which is not a whole lot of settlement. I'm going to box this. And that's the end of this problem. So it's a little bit of a long process, but it's not too hard. And there's just a little bit of, like I said earlier, going up here and making sure that you get the right values from your table. So we're going to keep moving on. And if you guys have any questions about this, please contact myself or any of the other TAs. So now we're going to do a little bit more settlement calculations. So we have a large embankment is to be built on the surface of a 15-foot clay layer. Before the embankment is built, the initial effective vertical stress at the middle of the clay layer is 480 psf. The result from an odometer test or a consolidation test on the clay gives us, circle these. One more shot. So I'm not covering everything. It gives us these parameters. And if the final sigma vertical effective stress at the middle of the layer after the embankment loading is 2100 psf, what is the settlement in inches of the clay layer resulting from this loading? So this is the equation we are going to use because it's going to be an over-consolidated clay. So, and this is equation 8.196, I believe. So we're using this. So let me change colors. So we're going to say SC. And we have this first term. So it's just 0.0352. And we need to be built on a surface of 15-foot clay layer. So we're going to say 15 feet because we're going to use the whole depth of the layer. Log of, well, we know sigma P prime is going to be this sigma V prime. So it's going to be 1800. And over, so we are given that at the middle of the clay layer, this 480. So we're going to use that here on the bottom. So this is part one, and I'm going to write part two down here. So we have C sub C epsilon, so that will be 0.18 times the whole depth of the layer, and then log of, well, now we're going to use this, this 2100, because that would be the addition of these two over our 1800. So when we do the math for that, we will find that we'll write this down somewhere else. So once we do the math up here, which we were given everything in this problem, I'm just plugging and chugging. And here we have, so this is the recompression index, and this is the consolidation index. And for over-consolidated clay, this is what we're always going to use. So when we do this math, we are going to find that the total settlement being induced is 0.4839 feet. And we typically, unless it's excessive settlement, we like to report settlement in inches. So total settlement is going to be roughly 5.8 inches. And this will be our final answer. So this one was pretty straightforward. Everything was given to you. So nothing too bad. So one more problem for the day. So now you get this all situated back. Shows a proposed, so this figure shows a proposed site where an excavation will be made. The 10-foot layer of sand will be removed so that the top of the 20-foot normally consolidated clay layer will be exposed. So we're going to assume full capillarity in the clay only. So assuming that the water table location remains the same during excavation, we need to compute the total vertical stress and the effective vertical stress and the pore water pressure values at the middle of the clay layer before and after excavation. And then assuming 1D consolidation, compute how much the clay layer will deform due to this excavation in inches. Specify whether this is settlement or heave. So we are going to address this as before excavation. Ooh, that is definitely not a straight line. There we go. So first things first, we're going to find our total vertical stress, which for the sand layer, it is 10 times 110 plus half, because we want to know in the center, half of the clay layer. So 12 times 120. So therefore, we are going to get 240 PSF. So now let's figure out the effective stress. So actually, let's do this, because remember I said in a previous recitation that a lot of these we can go about it any way we want, and you'll roughly get the right answer if you find a total stress first, or pore water pressure, or effective stress. So I'm just going to change things up a little bit, and we're going to find pore water pressure next. So we're going to say 12 minus 3 times 62.4 is going to give us 561.6 PSF. And continuing, now we're going to find our effective vertical stress, which is going to equal sigma v minus u. So we just have 2540 minus, 561.6. So this will equal 1978.4 PSF. And this is all, and remember, this is all before excavation. So now let's figure it out after. Let me write this in a different color. So let's do after excavation. So let's start off with the total vertical stress, which will be 12 times 120 equals 1440 PSF. And then we're going to find the pore water pressure, which will be 12 minus 3. And the pore water pressure shouldn't change because we're assuming that it stays exactly where it was. But this isn't a very realistic thing. But for this problem, this is what we're going to assume. And it's going to be exactly the same. And coming down here, I'm going to say vertical equals sigma v minus u. So now we're just going to take these two numbers. So this equals 878.4 PSF. So we got pretty much half of the problem done. So now for the second half of the problem, I'm going to write this in green now. And we know sigma V, between the two different sigma V's, we are going to say, well, 1978.4 minus this 878. So the difference, or the change in vertical stress between before and after excavation, will equal 1100 PSF. So normally consolidated clay. So that's what I'm going to denote normally consolidated. And you can find this equation 8.2 in your textbook, which I believe is page 353. And you'll find that the sigma p prime over the sigma v will equal 1. So here for this situation, we said, all right, sigma p prime equals sigma prime v. So we're going to say both of these in our initial condition equal 1978.4 PSF. So now I'm going to use this equation, which is also in your guys' textbook. I think this is page 369 or somewhere in that region. So using this equation, I'm going to plug and chug from what we've already found, 0.035 times 24 feet, which is for the whole clay layer, times the logarithm of 1978.4 over 878.4. So when we do this math, we're going to find that our swell is going to be 0.2962 feet, which equals 3.5 inches. And we are using this equation because normally consolidated clay means no compression curve, so no C sub C. So that's why we're using this. And yeah, so here is a little bit better of an example. This is what they gave us. And we're assuming normally consolidated, so we're only going to use that. So that's it for this problem. So I'm going to go down here, box our answer. And that's it. So if you guys have any questions, please let me know. And if you have any issues viewing the videos, please let me know. I really appreciate your guys' feedback. And for that, I'll let you guys enjoy the rest of your day. You guys take care. Bye.